Hello, students, subscribers, viewers, and future engineers. Here is part 3 of Algebra 2. This time, we devote ourselves to the solutions to problems on permutations, combinations, Pascal's triangles, binomial expansion, and set theory. All these topics are in Algebra 2. So, problem 1 is in part 2 already, so we begin with problem 2. So problem 2, find the sum of the coefficients of the terms in the expansion of quantity 4x minus 7y close raised to 4. So our guide is the sum of the coefficients of the general binomial for quantity ax to the p plus by to the q raised to n. And remember the formula, we just replace the variables by 1 because they cannot affect the coefficients, the values of the coefficients. So therefore, the sum of the coefficients for this binomial would be a plus b raised to n. So this is the guide, this is the general binomial, and the result would be quantity a plus b raised to n, where a is 4 and b is negative 7 and n is 4. So substitute quantity 4 minus 7 raised to 4, that's negative 3 to the 4th, and that is positive 81. Problem 3. In the expansion of quantity x to the 1/2 minus 3x to the negative 3/2 close raised to 12, find the constant term. The constant term is that term free of x, so x to the 0. The r term, because we do not know the position of the constant term, is a sub r n cm, remember, number of combinations of n things taken m at a time. First term raised to n minus m, second term raised to m. Where the first term, where n is 12, m we do not know, but that is r minus 1. First term is x to the 1/2, and the second term is negative 3x to the negative 3/2. So writing the formula first for the r term, NCM, first term to the n minus m, second term to the m, and we equate it to the constant term, which is kx to the 0. X to the 0 is of course 1, except x is 0, but there is value of x definitely. So therefore, we have n12, m unknown, first term x to the 1/2, n is 12, then second term negative 3x to the negative 3/2. So 12 cm, x to the 1/2 raised to 12 minus m, negative 3x to the negative 3/2 raised to m equals kx to the 0. So for the constant, there's no constant for the first term, but the second term has, then it can affect with the constant. So the constant term is 12 cm, negative 3 to the m. But we do not know m yet, so we find m first by equating the exponents of x. So let's simplify this. This is x to the 1/2 of 12, so x to the 6 minus m over 2 times x to the negative 3/2 m. So x to the 6 minus m over 2 times x to the negative 3/2 m equals x to the 0. Then simplifying the exponents of x in the left side, that's x to the 6 minus 2m is equal to x to the 0. Equating 6 minus 2m with 0, so 6 minus 2m equals 0, so that means m is 6 over 2 or 3. So having found m is 3, we then substitute it here because k is equal to this. So combination of 12 combination 3, or combination of 12 things taken 3 at a time, times negative 3 to the 3. So that would be, so 12 combination 3 is equal to 220, while negative 3 cubed is negative 27, multiplying So k is negative 5940. So this is the constant term. Problem 4, if the middle term of the expansion of quantity x cubed plus 2y squared close raised to n is constant, certain constant x to the 18, y to the 12, find that constant c. So our term again is NCN, first term raised to n minus n, second term to the n, and we equate it to this middle term here. So n is unknown, first term x cubed, second term 2y squared. The middle term position is also unknown, so n is unknown. So AR, NCM, first term to the n minus m, second term to the n, is CX to the 18, y to the 18. So substitute NCN x cubed raised to n minus n, then quantity 2y squared raised to n equals CX to the 18, y to the 12. So the constant C is NCM. There is no constant for the first term. So times 2 to the n. So that's the constant C. That's our guide, but we don't know n and m yet. So for the y, we can solve for m because this is y to the 2n equals y to the 12. So from there, equating 2m with 12, then m is 6. So m is 6. Then to solve for n, we have to equate exponents of x. So x to the 3x cubed raised to n minus 6 is times or equal to x to the 18. So equating exponents of x, 3 to the n minus 18 in the left side. So x to the 18. So 3n minus 18 equals 18, or 3n minus 18 equals 18, so 3n equals 36. So that means n is 12. Having found 12, we can now compute c. 12c 6 times 2 to the 6. 12c6 is equal to 924, while 2 to the 6 is 64. So obtaining the product, the constant is 59,136. Problem 5. If a multiple choice test consists of 5 questions with 4 possible answers, of which only one is correct, find point 1. How many different ways can a student check off one answer to each question? How many ways can a student check off one answer to each question and get all the questions wrong? So wrong answers, in other words. So for 5.1, we use horizontal bar method here. So n1 equals, we withdraw 5 blanks bars for the 5 questions. So in each question, there are 4 choices. So only one is chosen, but there are 4 ways to select an answer. A, B, C, D. So 4 here, then another 4 here, another 4, another 4, another 4. So that's 4 to the 5. So it is equal to 1024. For the second one, we check, we draw another 3 bars. And because all the answers are wrong, and there are 3 wrong answers from 4 choices, only one is correct. So in each bar, then because your answer is correct, you have chosen the 3 wrong answers. So 3 ways, 3 ways, 3 ways, 3 ways, 3 ways. And that is 3 to the 5. And 3 to the 5 is equal to 243 ways of committing mistakes. So therefore, the probability of getting 0 out of 5 by pure guessing in this quiz or in this test is 243 over 1024. If in case it's the probability of getting a score of 0 out of 5 by pure guessing. Of course, you have no idea about the choices, so you have to close your eyes to just answer by guessing, pure guessing. Problem 6, in how many ways can 5 different trees be planted in a row in a circle? So this is permutations in a row. So the formula is n factorial. Permutations of n things taken all at a time. So n factorial, in this case 5 factorial. So it is equal to 120 ways. For the second circular permutation, n minus 1 quantity factorial, and that is 4 factorial. And 4 factorial is 24. So there are 24 ways to plant 5 different trees in a circular way of planting. 7. How many ways can 6 people be lined up to get on a bus if certain 3 persons insist on following each other, if certain 2 persons refuse to follow each other? So for the first part, this is permutation by groups. We group the 3 and we have another 3 groups, but each group has 1 member. For the first group, there are 3 members. So G factorial, M factorial, and 2 factorial. So it's like arrangement of 4 different things taken all at a time. So 4 at a time because we have 4 groups of 4 factorial. But for group 1, we can, the members can be grouped in 3 factorial ways. There are 3 members, so 3 factorial ways. Group 2, 1 factorial, 1 factorial, 1 factorial. So therefore, n is equal to, there are 4 groups of 4 factorial times 3 factorial, the rest 1 factorial, 1 factorial, 1 factorial. So n is equal to 1,444 ways. In the second part, if certain 2 persons refuse to follow each other, if there is no restriction in lining up to get on the bus, then it's like arrangement in a row. So it is supposedly 6 factorial. But because 2 persons refuse to follow each other, then there should be gap between the 2 persons. The gap may be 1, maybe 2, or maybe 3, or maybe 4. It may be the first one and the last one, the 2. But because it's complicated, if you do that way, we analyze this problem as n factorial, supposedly the total number of ways for these 6 people to line up to get on a bus is 6 factorial. We just subtract the number of ways where they are following each other or they are next to each other. So let's group them, and the number of ways where they belong to one group should be subtracted from 6 factorial. That makes sense because they are in one group. So it is opposite to when they refuse to follow each other, right? So therefore, analysis is n is equal to n factorial minus the number of ways where we arrange them as groups, this formula here, so that it will be the number of ways where the 2 will be not following each other, or the 2 will have gap, at least 1 gap. So this would be the formula for this case, so that we can analyze. This is the 2 persons who don't want to follow each other, but let's group them. And there are 4 other groups. Each group of these 4 consists of only 1 member. So it's like there are 5 objects in a row. We can arrange them taken all at a time as 5 factorial. So that makes sense, so that you don't need to memorize this formula here. Then the fact that this has 2 members, they can interchange position, so they can be arranged within their group in 2 factorial ways, and the rest would be 1 factorial, 1 factorial, 1 factorial. So 6 factorial minus there are 5 groups, so 5 factorial times this group has 2 members, so 2 factorial, then the rest 1 factorial each. So 6 factorial minus 5 factorial times 2 factorial is equal to 480. So that's it for that problem. Problem 8, how many 3-digit numbers can be formed from the digits 0, 1, 2, 3, 4, 5, and 6 if each digit can be used only once if the number is greater than 330. Since the condition is the digit can be used only one, so 331, although that is greater than 330, is not qualified because that the digit 3 is repeated, 332, 333, 334, 335, up to 339. All those numbers are greater than 330, but they are not part of this 3-digit number greater than 330 because the digit 3 is repeated. So in short, we begin with 340. And what if the 3-digit number is greater than 300 plus? So therefore, we have to consider 2 cases here. The number should be greater than equal to 340. 340 is considered because 3, 4, and 0 are different digits and they are found in these digits here. And it should be less than 400, although 400 is not considered because 0, 0, the digit 0 is repeated. And for the second case, it should be greater than equal to 401. So let's consider first the first case, 3 digits, and this should be 300 plus. So greater than 340. I already explained that 331 up to 339 are not included because the digit 3 is repeated. And you look at the conditions. So to make sure that this is a 3-digit or 300 plus number and greater than 340, we should assign this first with 3. Specifically, this should be 3 so that it is 300 plus already. So 3, and there is only one 3, so there is only one way to assign a digit 3 here. So, but less than 400, remember. Then, after we assign a digit here, which is definitely 3, there's only one 3 here, so this is 300 plus. The next position should be greater equal to 4, and 0 is not qualified, 1, 2, and 3. 3 is not qualified because this is specifically 3, and if that's so, 3 is again repeated. So 0, 1, and 2 are also disqualified because they will be less than 330 definitely. So it should be, the next digit should be 4 and greater than 4 so that it is 340 plus, or even including 340, right? So there are 3 digits greater equal to 4, which are 4, 5, and 6. So there are 3 ways to assign a digit here, which is definitely greater equal to 4. So these 3 here would be 4, 5, or 6. Then, after assigning a digit here, which is only 1, 2 have been signed. And the last digit may be any digit because we are sure that this is greater equal to 4. So this may be 0. So for instance, if this 3 ways here, it is 4. So the digit would be 340, and 0 is possible because this is greater equal to 340 and it is greater than 330. So that's why the remaining digits is 5, 2, 4, 6, 7. There are 7 originally, but we have assigned 2 digits already, so the remaining digits is 5. So there are 5 ways to assign a digit in this remaining position. So by fundamental principle of counting, N1 is equal to 15. 3 times 5. 1 times 3 times 5 is 15. If you want the details for this 15 here, I will state them. So these are 340. That's the first. 341, that's the second. 342, that's the third. 345, 344 is not qualified because 4 is repeated. 345, that's the fourth. 346, right? So that's the fifth. So this is 15. So 10 more. Next is, it is 400, 350, 350 qualified. 351, that's the seventh. 352, the eighth. 353 is not included because 3 is repeated. 354, that's the ninth. 356, that's the 10th. 355 is again not considered. So 10, 5 more. 360, that's the 11th. 361, 12. 362, 13. 363 is not qualified. 364, that's the 14th. 365, that's the 15th. Oh, so it's really 15. Then for the second case, N2 should be greater equal to 401. We should base it to 401 because 400 is not qualified because 0 is repeated. So this should be greater equal to 401. So that this is surely greater equal to 401, we should assign a digit here which is equal and greater than 4. There are 3 digits that are equal and greater than 4. The 4, 5, and 6. So there are 3 ways to assign a digit there. So if it is 400 plus, no problem because 401 is possible, right? 402 is possible. 403 is possible. 404 is not qualified. So there are 3 ways to assign a digit here. Those are 4, 5, and 6. Definitely this is greater than 401. This may be 500 plus. This may be 600 plus. Right? So other numbers, 3-digit numbers greater than 401 like 700 plus, not included because there's no 7 here, there's no 8 here, there's no 9 here. So 700 plus, 800 plus, 900 plus are not possible because of the given digits. So after assigning a digit here, there will be 6 digits left and all the 6 can be assigned here. So there are 6 ways to assign a digit here, but only 1 is assigned. So 2 numbers are already assigned, 5 left. So there are 5 ways to assign a digit in the remaining position. So by fundamental principle of counting, 3 times 6 times 5 is 90. Therefore, the total number of 3-digit numbers greater than 330 without repeating the digit is equal to 15 plus 90 is 105. So problem 9, how many ways can one president, one vice president, and one secretary be chosen from 14 PICE members if no one can hold 2 positions? So this is permutations of 14 members taken 3 at a time. So 14 P3 is 14 factorial over quantity 14 minus 3 factorial, or the shorter way is by fundamental principle of counting, 14 times 13 times 12. Because after we choose one president, there will be 13 qualified nominees left. Then after choosing vice president, there will be 12 nominees left. So 14 times 13 times 12 is the same as 14 factorial over quantity 14 minus 3 factorial, and that is equal to 2184. So there are 2184 ways. 10, how many different permutations can be made of the letters of the word infinity. So this is permutations in which some things are identical of the first kind, and other things are identical of a second kind, and so on and so forth. The formula is n factorial divided by r1 factorial, r2 factorial, dot. So where r excuse me, where r1 is equal to I, so I factorial, then divided by n, r2 is n factorial. So n factorial over I factorial over capital N factorial. N is 2, 4, 6, 8, 8 letters. I, there are 3 I's, so 3 factorial. Letter, capital letter N, 2, so 2 factorial. So 8 factorial over 3 factorial times 2 factorial, and that is equal to 3,360. Problem 11, find the sum of the coefficients in the expansion of quantity 4x minus 3 raised to 8. Our guide is the general binomial ax to the p minus constant raised to 8. The sum of the coefficients is a plus k raised to 8 minus quantity k to the 8. If you can recall, to neutralize the effect of the constant raised to 8, which is accounted as a coefficient, which is supposedly none. So a is 4, k is negative 3. So that would be 4 plus negative 3, or 4 minus 3 raised to 8 minus quantity negative 3 to the 8. And that is equal to 1 minus positive, this is positive, so 1 minus positive is negative 6,560. 12, in how many ways can the letters of the word boob be arranged if all letters are taken each time? So this is the same as problem 11, as problem 10. So 4 factorial over 2 factorial, 2 factorial, b factorial is o factorial, 2, 2. So 4 factorial over 2 factorial, 2 factorial, and that is 6. If you want this 6, so remember that's a boob. Because that's a boob, what do we do? Ub-ubon. So ub-ub. But don't rush, kay if you rush, this will happen. Maubulo ka. So don't rush. Enjoy and relax, and of course enjoy, so that this would be the feeling baby oh oh, then oh oh baby, then only the bobos will do that. So you cannot be called bobo. Do not let your boob be done by that way. So these are the 6 different arrangements to show that there are really 6 different arrangements when we arrange the word book, taken all the letters each time. So there are 6 different ways. So 13, in how many ways can the books in math, hydraulics, and structural engineering be arranged on a shelf if math has 3 volumes, hydraulics has 2 volumes, and structural engineering has 4 volumes? So this is again an application of permutations by groups. You don't need actually to memorize that. There are 3 groups in a row, so we can arrange them in 3 factorial ways. But each volume of each group can be arranged also in the number of books factorial. So therefore, we have g factorial, m1 factorial, m2 factorial if you use the formula, but there's no formula here if you understood the principle on permutations. So 3 factorial, then math 1 has 3 volumes, so we can arrange volume 1, volume 2, volume 3 in math in 3 factorial ways, hydraulics 2, so 2 factorial, and then in structural engineering 4 factorial. So getting the product n is equal to 1728 ways. 14, if repetitions are not permitted, how many 3-digit even numbers can be formed from the digits 1, 2, 4, 5, 7, 8, and 9. So 2, 4, 6. There are 7 digits given here. How many different 4-digit integers can be formed if they are to be greater than 6,000? And how many different numbers can be formed from the given digits or integers if they are to be greater than 900,000 and of different digits? So meaning repetitions not allowed. So for the first one, three-digit even numbers, a number is even if the last digit is even, right? So that's the guide. So we must determine the number of ways in assigning the last digit, and it should be even. So we draw 3 horizontal bars because it is definitely 3-digit number. So there are 1, 2, 4, 8. These are the even digits. There are 3 available even digits. So there are 3 ways to assign an even digit here. After assigning an even digit here, it doesn't matter here because definitely, because this is surely even, then even if the 2 positions here are assigned with odd numbers, that is still even. So after assigning an even digit here, but only 1 is assigned, there will be 6 digits left. So there are 6 ways to assign a digit here, then 5 left. So 5 digits in assign 5 ways in assigning a digit here. So by fundamental principle of counting, 6 times 5 times 3, that would be 90 ways. For the second one, we draw, because this is mentioned 4-digit integers, we draw 4 bars. And it should be greater than 6,000. To make sure this is greater than 6,000, we should assign this digit there first. And this should be greater equal to 6, because this is already 1,000. And only 3 digits are greater than 6, 7, 8, and 9. So there are 3 ways to assign a digit here which is greater than 6. So 3. So after we assign a digit here which is definitely greater than 6, there will be 6 digits left. So there are 6 ways to assign a digit here. No more problem with this because we are sure that this is greater than 6,000 already. It may be 7,000, 8,000, or 9,000. So 6 left, 5 left, 4 left. So 3 times 6 times 5 times 4 by fundamental principle of counting, that will be 360. Then for the last question, how many different numbers can be formed from the given integers if they are to be greater than 900,000? So we draw 6 bars. There are 2 cases here. One is 6-digit, and that is 100,000, right? But it should be greater than 900,000. Luckily, there is 9 here. So if we assign the first digit, this is 900,000 plus definitely, because the rest would be greater than 0. But there is only 1 digit which is greater equal to 9. Of course, there's no other. So there's only one way to assign a digit here. The second case is if it is a 7-digit number, or yes, 7-digit number, and that is millions. For the second part, there's no problem anymore because it is millions, and millions are greater than 900,000. So since there are 7 available digits, then for the second case, it is just 7 factorial. So let's consider the first case. So only 1 is assigned here, because it should be greater than 600,000, 900,000 rather. So 1, that is digit 9. The rest 6 because there will be 6 digits left. 5, 4, then here 3, then here 2. 6 times 5 times 4 times 3 times 2 by fundamental principle of counting, because the next supposedly is 1, is like 6 factorial. So 6 times 5 times 4 times 3 times 2 is the same as 6 factorial. So NA is 6 factorial. The second case, 7 digits, that's millions, that is definitely greater than 900,000. So that would be 7 factorial. So therefore, the total number of ways is 6 factorial plus 7 factorial, and that is equal to 5,760. Problem 15. In how many ways can 5 engineers and 4 nurses be arranged in a round table if the nurses insisted to be sitting side by side? So if you draw the figure, it seems that there is issue here about the because the nurses insisted to be sitting side by side. Notice that the engineers are also sitting side by side. So let's twist the problem. The nurses are guys, males. Engineers are women and beautiful. So this is a one-sided problem. They thought that the engineers are all males and the nurses are females. Remember, there are also male nurses. So this problem can be twisted. So this is permutation by groups, but circular permutation. The formula is we adjust G minus 1 factorial, M1 factorial, M2 factorial, dot, dot, dot. There are only two groups, engineers and nurses. So therefore, we have quantity 2 minus 1 factorial, or that's 1 factorial, then 5 factorial, 4 factorial, 5 engineers, 4 nurses. So n is equal to 2880. So there are 2880 ways to arrange these 5 engineers and 4 nurses in a round table. 16. There are 36 lines that can be drawn from an n-cornered convex polygon. how many corners are there all in all? Take note that if there are 2 points, points 1 and 2, if we draw a line from point 1 to point 2, that's the same line, same combination, same line. If we draw from point 1, if we draw a line from point 2 to point 1, right? So same line can be drawn. So therefore, this is a problem on combinations. And the formula is n combination 2, because 2 points determine a line, equals 36. And since NC2 is n factorial over n minus 2 factorial, or NCR is n factorial over quantity n minus r close factorial times r factorial. So this is n factorial over n minus 2 factorial times 2 factorial equals 36. 2 factorial is 2. And we can write n factorial as n times n minus 1 times n minus 2 factorial, so that we can cancel n minus 2 factorial. And 2 factorial is 2, so we can cancel that. Then distribute n squared minus n equals 2 times 36, 72. Transpose 72 to the left. So we have n squared minus n minus 72 equals 0, which can be factored into quantity n minus 9, n plus 8 equals 0. So n cannot be negative, so n equals 9. 17. In how many ways can a panel of 5 judges declare a winner in a beauty contest? So this is combinations, because if judge 1, 2, and 3 will decide with the same decision, 2, 3, 1, 3, 1, 2, so they are the same judges. So this is problem on combinations. So to declare a winner in the beauty contest, 3 judges out of 5 must have the same decision. So that's majority. 4 out of 5, and unanimous decision, 5, all of them have the same decision, 5 out of 5. So therefore, this is equal to 5C3 plus 5C4 plus 5C5. 5C3 is 10, 5C4 is 5, and 5C5 is 1. So n is equal to 16. Then problem 18, how many subsets are there in the set STILHOP? So there are 2, 4, 6, 7. The formula is 2 to the n number of subsets, and 2 to the 7 is 128. Can we use the formula here, 2 to the n minus 1? We can. But we subtract further 5C2 because that's not majority, and 5C1 because that's not majority. So another way of solving this problem, it is equal to 2 to the 5 minus 1, then minus 5 combination 1 minus 5 combination 2. The minus 1 is for 5 combination 0, which cannot be because there are really 5 judges. So that's the other way of solving this problem 17. So let's proceed to the second to the last. What is the coefficient of the fifth term of the expansion of quantity 2x squared plus 3y cubed raised to 10? Then how about the sum of the exponents of the terms in the expansion? So for the coefficient of the fifth term, formula for R term is NCM, first term raised to n minus m, second term raised to m. And we are only looking for the coefficients, but we can determine the entire term. N is 10, m is fifth term minus 1, so 4. And that's it. The first term is 2x squared, the second term is 3y cubed. So fifth term is equal to 10 combination 4, 2x squared raised to 10 minus 4, then quantity 3y cubed raised to 4. Expanding 10c4 is equal to 210, then 2 to the 6 is 64, then x square quantity to the 6, 2 times 6 is, so that's why we have x to the 12 here. 3 to the 4th is 81, 3 times 4 is 12, so that's why we have y to the 12. We are not interested of the fifth term, we are interested only of the coefficient of the fifth term, and that is 210 times 64 times 81. And that value is equal to 1,088,640. Finally, 20, because the video is long. Combination lock has 60 different positions. To open the lock, the dial is turned to a certain bit number in the clockwise direction. Then to a number in the counterclockwise direction. And finally, to a third number in the clockwise direction. So if successive numbers in the combination cannot be the same, so how many different combinations are possible? So take note, in the first rotation, there are 60 different positions, so there are 60 ways for the first combination. So 60 ways. Then in counterclockwise direction, because no number should be repeated in successive way, so there will be 59 options left. So 60 times 59. So 60 times 59. Then, since there will be no repetition successively, so and there are 59 available, there are 59 available again because the original is 60. So times 59 again. So that's it. So 60 times 59 times 59 from the fundamental principle of counting is equal to 208,860.